Morning, nerds. Wow. Reset? No, I want all of you to hear how boring that was. Alrighty, well, anyway, thanks first period. Well, what we're going to do is we are going to go ahead and dive into properties of logarithms. I don't really know why the authors called this properties of logarithms, because there's some really important properties not included in this lesson, must be included in a future lesson. That's okay, though. We're going to use properties of logarithms today to solve some basic logarithmic equations. We're going to have factoring skills from Algebra 1 to be successful. And then after we've done that, we'll introduce some actual properties that you didn't know existed for logarithms. And then we'll use those to solve some more crapola. And then eventually we'll work our way into word problems and stuff like that. Okay? Okay. There's no way we're finishing this lesson in one day, so there's no rush to get the homework done in one night. But please do as much of it as you can after the first lesson. Okay? All right. Cool beans. Here we go. Solving logarithmic equations. First things first, trying to get x by itself. Unfortunately, x is hiding inside of a log base 4 class. Let's see if you remember how this works. Class. What cancels log base 4? Okay, they might have heard some of you on the video that time. Exponential base 4 is what's going to cancel log base 4, so we're going to use exponential base 4 on both sides of the equal sign. So we're going to put a big base 4 here, a big base 4 here. Pause the video while I let that late person in. Never mind. Okay, let's see, because I was going to give Samantha a hard time for being late, that's why. No, I said Samantha. See, all this is recording, though, so she's the only one not here. Anyway, what we're going to do is we're going to say log base 4 cancels exponential base 4 on the left side, and that gives me x equals 4 raised to the 5 over 2 power. That means you're going to need to be good with fractional exponents, which is chapter 5, the stuff we did before the break. You must be good with these. Anybody remember what the 1/2 power means? It means square root. So this is what this actually says. Square root of 4, and then raise that number to the 5th power. The square root of 4 is 2. And 2 to the 5th is 32. There it is. So it's crazy how those old skills keep coming up and are important still, isn't it? But that's it. So what property of logarithms did we use? The fact that they're inverses of exponential bases. That's the property we used. Okay. Very simple. Questions, comments, concerns, or straightforward? No big deal, right? Hardest part about that should have been remembering how this works. You know, if you're not so hot at remembering that fractional powers act as roots, a way you could have gotten around it would have been to say that 4 was 2 to the 2. And when you raise a power to a power, you multiply the exponents. Ten over 2 is 5. Could have got around it that way if you didn't remember how radicals and exponents work, but just throwing it out there. That won't always be there to save you, but with a question like this, it would have worked. It's just a workaround, just showing you. Alrighty, next. The x is buried inside a logarithm class. How am I going to make that log base 3 go away? Exponential base 3. We're going to work on our chorus. So we're going to use an exponential base 3 on both sides. On the left side, the base 3 and the log base 3 cancel and leave behind that 2x minus 6. But on the right side, I have 3 to the 1st power. 3. Now we're getting x alone. Add 6 to both sides. I don't think I need to show that work, but I will anyway. Then divide both sides by 2. Eke a fraction. You'll be okay. You know what we do have to always make sure that we're watching out for, though? Extraneous solutions. Any structure that has a restricted domain has the ability to generate extraneous solutions when we cancel the structure. Just like square roots did. You have to always make sure that your domain remains positive. Because the moment you canceled the log base 3 on both sides, you eliminated restrictions that the structure creates. So when we solve logarithmic equations, you must always make sure that your answers were allowed. Always make sure that an answer did not make a domain 0 or negative. Not a domain, an argument. Arguments of logarithms must always be positive. So this number is 4.5. If you double 4.5, you get 9, and 9 minus 6 is not negative, so we're okay. The answer is fine. Okay? Okay. Yes. Boop. This one has log base 5 on both sides. And x is buried inside the logarithm on both sides. So how am I going to cancel that log base 5, class? Ooh, the chorus was much better that time. Exponential base 5 on both sides is how we're going to make it happen. So we use an exponential base 5 here, and exponential base 5 here, and the log base 5s and exponential base 5s cancel each other out. That leaves me 2x squared minus 6 equals 4x. Yay, a quadratic. Yay! I love quadratics. Solved by factoring. Of course, you can't solve a quadratic unless it's set equal to 0. So what you are going to have to do is you're going to have to subtract 4x from both sides first. Get you 2x squared minus 4x minus 6 equals 0. And this is an Algebra 1 question now. What do I need to do first? Michael, got an idea for me? How so? What do you mean by simplify? Ah, yes. Michael notices that there is a GCF that is just a number. And since there's a GCF that's just a number, it won't affect my solutions if I simply divide it away. If it was an x, I wouldn't be able to just divide it away because, you know, x's are where my solutions come from. I would need to factor it out as a GCF. If you're concerned about knowing when you can and cannot simply just divide a number away, then just always pull GCFs out. When you're factoring, you should always be on the hunt for GCFs, and good on Michael. Notice we have a GCF of 2. Tell you what I'm going to do. I'm not going to divide it. Instead, I'm just going to factor it out to the front as a GCF because we'll never get in trouble by doing that. What you said will work just fine. But I don't want people to have to memorize when that works and when it doesn't. Okay, thank goodness there's no number in front of x squared, so this is one of the easy ones to factor. We're just looking for two numbers that multiply to -3 that add to -2. -3 and +1 will do it. So we have two solutions. We have x equals 3 as a solution, because that gets me 0. And we have x equals -1 as a solution, because that gets me 0. At the very end, I know you're thrilled you solved something by factoring, you're clicking your heels, you're ready to go to the next question. You must always make sure your answers don't break the rules. And the rules are, the argument must be positive. So right here, this argument does not allow x to be negative. And because this argument does not allow x to be negative, this answer is extraneous. We have to make sure that we don't break rules with the 3 as well. 3 squared is 9, and doubling 9 gets me 18. 18 minus 6 is positive. So we're fine. Assuming we did all our algebra correct, we're fine. So there, for the very first time, you've seen an extraneous solution. Eleanor, what's up? Well, you have to make sure that your solutions work for both arguments. The moment a solution breaks the rules of a single argument, that solution's garbage. And so it doesn't need to fail everywhere. It doesn't need to be successful. Like, in order to work, it has to be successful everywhere. But we know that 3 is allowed here because 4 times 3 is positive. So we were just making sure it was still positive here. The moment this failed, we stopped worrying about it. So, Mr. M, is it possible to get 2 solutions that work? Absolutely. Is it possible to only have 1? Obviously. Is it possible to have none? You know it. Is it always the negative answer that's bad? No, it's not. This question it just worked out that the negative answer was bad. So my answers are always positive. No, sometimes answers are negative. Your job is just to make sure that when you substitute it into the argument stays positive. For example, pretend for a moment that said negative 4x in there. If that said negative 4x, the only x's that would have worked would have been negative numbers, because negative 4 times a negative number is positive. So I don't want you thinking that just because an answer is negative, it's extraneous. And I don't want you thinking this answer is extraneous because it's negative. Those were 2 different statements, and they mean 2 different things. Your job is make sure an argument is never 0 or negative, no matter what. Cool? Yay? Okay. Question D has a typo in it. There, it's fixed. I typed a minus sign by accident. It was supposed to be a plus sign. And you know the only reason why I know that ahead of time is because I went to make the answer key for the homework yesterday and didn't pay attention to what I was doing, and I was making the answer key to the notes. And I got all the way to this question before I realized this question's broken. Crap, my homework is bad. And then I was like, wait a minute. These are my notes. Oh, okay, that's easy. I'll tell them all in person to fix it. So hopefully there's no typos on the homework. But yeah, I found that because I was making an answer key for what I thought was the homework, and it was actually these notes. These notes. All right, so just like the last question, both of my arguments have x's in them, and I have a log base matching thing on both sides of the equation. So class, how am I going to make this log base 3 go away? Yeah, exponential base 3 is going to do it. So I'm going to use an exponential base 3 on both sides of the equation, which makes the logarithms disappear. And again, we are at an Algebra 1 question, to be honest with you. What color do I want to write in? I write in green. I haven't written in enough green today. 2x squared plus 5x, not minus. Minus 4 equals 6x minus 1. You have to bring everything to one side. Subtract the 6x. Add the 1. And unfortunately, there's a number in front of x squared that is not a GCF. So we're going to have to know how to factor quadratics, like you needed to know how to factor quadratics in Algebra 1 and in geometry. You have to know how to factor. I'm a big fan of the Lizzie method. I've showed it a bunch of times in notes, but in case you've forgotten, because your generation likes to learn and burn, thinking that the material is not going to be important in the future, I'll reteach you the Lizzie method. The way it works is you take this 2 and you multiply it to this negative 3. That's going to alter the equation. That gives you a new quadratic. It gives you this quadratic. X squared minus x minus 6 equals 0. You see I've written it in a different color because it's no longer the same quadratic. I took this number, whoa, watch out. I took this number and I multiplied it to this number, and that's how I got this. Now we can factor this blue one using a regular easy method for factoring. What 2 numbers multiply to negative 6 that add to negative 1? Negative 3 and positive 2. I altered the equation, did I not? And I altered that equation by multiplying by 2, correct? So it's time to unalter the equation by dividing that 2 back out. That's how the Lizzie method works. Now I can write it back in green because now that I've actually divided out the 2, I'm back to factoring this thing. Or at least solving by factoring. It's technically not finished factoring until you move this 2 in front of this x. But the reason why I like, so it would have been 2x minus 3 and then x plus 1. But the reason why I like solving using the Lizzie method is because I can see right now what 2 values for x work. Positive 3/2 and negative 1. So one more time, technically I didn't finish factoring. I'd have to take this 2 that's right here and move it in front of this x. So this would have said 2x minus 3, x plus 1. But there's no reason to do that because we're solving. So we can see that the answer would have been positive 3/2 and negative 1. Now your job is to go to the 2 arguments and make sure the argument remains positive when you plug it in. I know everybody's instantly looking at that negative 1 and thinking, I bet you that's a bad number. It's like number racism. So you look at this negative 1 and you go right here and you go, oh crap, 6 times negative 1 minus 1. That is definitely a negative number. So that is extraneous. Let's make sure 3 over 2 works. 6 times 3 is 18. 18 divided by 2 is 9. 9 minus 1 is positive. Cool. It still works. Ew. Is it going to work here? Well, 3 over 2 squared is 9 over 4. 18 over 4 plus 15 over 4. Excuse me, 15 over 2. All of those numbers are bigger than 4. So you can sit, is someone going to answer the door like someone knocked a while ago? Anyway, it's going to be positive still. So we're in good shape. I could have sworn somebody knocked. Was one of you tapping on the table over there? Somebody tapped on a table or something. Anyway, the answer works just fine. We're in good shape. Strem, that's another question that, had only one answer and the negative was the bad one. Are you sure that's not always the case? I'm sure that is not always the case. I promise you, you have to double check. Sometimes there's no solutions. Sometimes the negative ones work. Sometimes the positive ones don't. You always check. Gracie. Ooh. So Gracie wants to know what happens if the logarithms have different bases. She wants to know, is that possible to solve? The answer is yes, it's very possible to solve. Not yet. You have to learn more. You will, but it requires a property of logarithms that we learn later in the chapter. It's called change of base, which literally allows you to change the base. You'll see. I can tell you it's not as pretty. It gets really messy, but yes, you can do it. And yes, we will do it. Caroline's mind is blown. Okay. It's a good question, though. Alrighty. Just like question B, there's only a logarithm on one side. All right. Let's cancel this log base 2. Class, what cancels log base 2? Exponential base 2 will do it. So we put a big exponential base 2 on both sides, and we go Gators, orange and blue. We allow exponential base 2 to cancel log base 2. What have I not written in enough of? I don't have a pink. I guess I'll go back to blue. X squared minus 6x plus 9 equals 2 to the 2. 4. Subtract 4 from both sides, please. I need 2 numbers that multiply to 5 that add to negative 6. -5 and -1. It gives us two positive solutions, x equals 5 and x equals 1. Let's see if they both work. Let's take this 1 and plug it in. 1 minus 6, -5. Oh, but -5 times plus 9 is positive, so we're safe. Let's see if 5 works. 25 minus 30, -5. Oh, but -5 plus 9 also works. So we're in good shape. This one does have two solutions. There you go. They both work. How about that? You see, I like all of my questions to be slightly different. They show you something slightly different. The first one showed you how to remember how to use fractional exponents. The second one showed you what happens if there's only a log on one side. The two in the middle showed you how to factor, reminded you that you could end up with quadratics, but one of them required the Lizzie method, the other one didn't. And the last one showed you a quadratic that actually did get you two answers. So you see they're all a little bit different. They're all showing you something slightly different. So let's flip the page. And a box, you guys probably realize by now that boxes are information in my notes. These are true properties of logarithms. And there's more than three, but these are the first three that you learn. The product rule, the quotient rule, the power rule. I need a piece of scrap paper. Because I'm going to ask you a question. What happens when you multiply two numbers with the same base? Add the exponents? Oh, okay. Here's me multiplying two numbers. They have the same log base. Here's me adding the exponents. This is the exact same rule written in logarithmic form instead of written in exponential form. And I can prove it to you. If I use a log base x on both sides of this, well, I don't want to say it like that, not log base x. If I used, how do I want to say this? Crap, I should have thought ahead of that. Well, anyway, can you all at least see that it is the same property, just in log format? That it's me multiplying, I should have used b's instead of x's, and I'm having trouble showing you an example like that. But what this tells us is, when we have multiplication in the argument, this can be split into the addition of two logarithms. And it's because of this property. So this is just the logarithmic version of this property. Do you guys remember what happens when you divide two numbers with the same base? You subtract the exponents, correct? Here is the logarithmic version of that property. It's showing you when you divide two numbers that have the same log base, you can actually subtract the logarithms. And just like here, how it was top minus bottom, it's still log top minus log bottom. So it's the exact same property, just in logarithmic form. When you have a quotient in the argument, when you have division in the argument, this can be written as the difference between two logarithms. And it's always top minus bottom, just like it was here. Comfortable? Still okay? Power to power, what do? Multiply. Here, the argument has an exponent. This argument exponent can be moved to the front and be used to multiply 2 log base b of m. So it's the same property, just in logarithmic format. And we use these three properties to do a lot of things in mathematics. All right? Because these properties are true backwards and forwards. Before we use them to backwards and forwards, let's use them to help us evaluate some things. And I could ask you to do this without a calculator, which means if this goes on a test, it'll be on the no calculator portion. Do I know what log base 2 of 5 is on the regular? No, I don't. I used a calculator. Log base 2 of 5 is about 2.322. And we're going to use that truth to figure out what the value of this is. So we can estimate the value of log base 2 of 20 using the estimated value of log base 2 of 5. But how, Mr. M? Very simple. 20 is 4 times 5. And a moment ago, we just saw that when you have multiplication in the argument of a logarithm, that can be split into the addition of 2 logarithms. Hey, my phone is ringing. That's not interruptive at all. Anyway, what was I saying? I think I said the word interruptive a minute ago. That's not a word. What I meant to say was disruptive. It's not a word. Anyway, I was trying to say that when you have a multiplication in the argument of a logarithm, this gets split into the addition of 2 logarithms like this. And we have the ability to evaluate log base 2 of 4. And it would be great if I said class, if everybody could answer me at the same time. So, hey class, what is the value of log base 2 of 4? Okay, I didn't get a whole class of voices. What that tells me is I still have a number of you that do not know how to evaluate logarithms, which would explain why that basket over there does not have a whole bunch of extra credits turned in. Scary. It says, what power of 2 gets me a 4? The second power of 2 gets me a 4. And we know, because it says so, that log base 2 of 5 is approximately equal to 2.322. Which means this logarithm value is approximately 4.322. Ta-da! Here, what we have is a fraction in the argument. Fractions! Well, hey, you know, if you guys don't like fractions, you should love logarithms. Because logarithms, when they have fractions inside, can be written without fractions. Look, no more fractions. And we have the ability to evaluate this. Let's try it again. Hey, class, what's the value of log base 2 of 8? Hey, more voices that time. All right, so cool. Maybe we just weren't used to me asking you to actually evaluate something. Log base 2 of 8 is 3 because it says what power of 2 gets me an 8? The third power does. And 3 minus this, which is 2.322, is going to give us, well, it's approximately 2.322. You know, it's an approximation. Let's see. I'm going to let's see, I almost need 0.7. I almost need 0.78. But I can't use 0.78, so it's going to be 0.778. There it is. If you're not sure, you could add 322 to 778, and you'll see that you get 1. Don't correct me when I'm wrong. Yeah, it is 6. Sometimes subtraction's hard, okay? Stop making fun of me. Anyway, degree in mathematics, can't add and subtract. This, 125. 125, what's significant about that number? It is a power of 5. What power of 5 is it? It is a third power of 5. It gives us this, log base 2 of 5 to the third. And we just learned from this box up here, the logarithmic form of, power to a power. And it basically says, hey, you got a power in your argument? Move that bad boy to the front as a multiplication. And we were given the approximation of log base 2 of 5. It's 2.322. So we're going to say that this is 3 times 2.322. See, 3 times 2 is 6, 3 times 2 is 6, 3 times 3 is 9, 3 times 2 is 6. Ta-da! There it is. Isn't that neat? So knowing one logarithm, at least its approximation, allowed us to evaluate 3 more ridiculous logarithms. Cool.
Wait, so that's maybe only for the calculator?
Yeah, why not? I didn't need a calculator to do any of that, especially not this purple one. But I mean, in all reality though, all we did was add, subtract, and multiply. I made sure you didn't have to carry. It's just literally add, subtract, and multiply. It's that easy. And yes, you're going to have evaluating logarithms on the no calculator portion, like you had on the extra credit. There'll be things like that on the no calculator portion of the test. Scoop. So what else can these rules be used for? They can also be used to expand logarithms, like you saw here, without knowing any evaluation or what they're equal to. They could just literally be used to split logarithms up. There's no base on this log. Do you guys remember what that is? I gave you the sneak peek of that. That means it's log base 10. For now, I'll try to remember. I'm pretty sure every time I did log base 10 in the homework, I'm pretty sure I typed the 10. But I'm not going to lie. I copy and pasted these notes from a different, actually from pre-calc honors. These 2 questions are for pre-calc honors. So they say log, meaning base 10. I'm going to write the base 10. Okay? Well, in fact, let's squeeze it in there right now. Boop, right there. And right here. Boop, like that. And I just realized you've never seen an ln, have you? Oh, man. I'm so bad at this job. If that shows up on the homework, replace it with log. If you see ln, replace it with log, okay? Because I teach 3 different courses, and I'm going to be real with you, all 3 of them are doing logarithms right now. It's hard for me to remember what stuff I've said to what classes sometimes. Anyway, let's expand this. That means break it apart, get it as fully blown apart as possible. Use every one of these properties that you can use and try to get every single logarithm to have one thing in it if possible. First, what you're going to see is multiplications. There are 3 objects being held together with multiplication dots in there. That means it can be split into 3 logarithms with plus signs in between them. Log base 10 of 8 plus log base 10 of x plus log base 10 of y to the 4th. But this is not fully expanded. Reason why is this guy right here can move to the front of its logarithm. Then it's fully expanded. There you go. Yes, ma'am. Why doesn't it move to the front of the whole thing? What a good question. Let me ask you. Does this x have an exponent? No. If you move it to the front of everything, you're implying that everything within that argument has that power. If I had put this 4 on the outside of these parentheses, then we could say everything in the argument has that power, and that 4 would have been on the front of every one of these logarithms. But because it's only on one piece of the argument, it will only be on one of the logarithms when it's expanded. Great question. Any other questions on that? That was a good one. We okay here? All right. Then let's scoot down to another expanding question. Do I have a brave volunteer that doesn't mind being wrong, that wants to help me do this question? Caroline immediately said no. I'm going to pick on her just because she said no. No, I want you to get close to the microphone and say, I'm too scared. Come here. Say it out loud. Say, I'm too scared. It's okay what? She's too scared. Come on, someone talk to me. Someone help me. You're not afraid of being wrong. I appreciate you, but you've already told me I was wrong today, so I'm mad at you. Who else? Come on. Okay, Julian A. Appreciate you, my guy. I'm kidding, you know. Please let me know when I make mistakes. Julian, let's try to expand this bad boy. What would you do first? Do it in multiple steps. Don't give me the answer, okay? Okay. Log base 10 of 8. Yes? Where'd the y go? Let's do it in one step at a time, okay? Let's do it like that first. So yes, we have used our quotient property, which by the way, I don't need you to know the name of it, but we've used the quotient property to take this fraction apart and make it the subtraction of 2 logarithms, okay? Now, Julian, because I wanted to have, that's why I said don't just give me the answer. Now, continue to expand. We know we're not finished because I have a multiplication here. So, continue from here. Yes, sir? Okay. Thank you, Julian. Now here's what I want to know. Who can tell me why this answer is not right? And Julian, thank you. I needed it in the notes. Okay, Gracie, give me a. What do you think? So she says because this one's positive, and what do you think it should be? Negative. Is that what you were going to say? So the problem that we're having here, and both ladies, fantastic. So you told me what the issue is, and you told me how to fix it. Fantastic. The issue is this y came out of the bottom of the fraction. Imagine the x wasn't there. He would have said log base 10 of 8 minus log base 10 of y. Right? Because it came out of the bottom of the fraction, it needs to be minus that number. So what we can do to fix it is use parentheses. Because yes, this multiplication can be split into an addition. But the whole multiplication came out of the bottom. Then distribute the negative sign. Basically, if it is in the bottom of a logarithm's fractional argument, that was a weird thing to say, it must have a negative sign in front of it. And you want to know why? I could treat this minus sign right here as a plus negative 1 log base 10 of y. Which means this multiplier could have been an exponent. And anything with a negative exponent moves across its own fraction bar. So there we go. All three of you, thank you so much. And the last one for today, which is what I just showed you here actually, is called condensing. turning it back into, if you can, a single logarithm. Okay? First things first. Did you notice in this question, the last thing I did was move the exponents to the front? That's when you're taking it apart. So if you're putting it back together, that's the first thing you have to do. You would have to first move any multiplier back to the exponent of the argument. That is going to give me, I'm sorry about the lack of space down here. I really need to do a good job with the space on this. Log base 10 of x to the 5th minus log base 10 of y squared minus log base 10 of z squared. And just a moment ago, we saw this use of parentheses. So if you wanted to show all the work, it would look like this. These would condense to a single logarithm. That was multiplication in it. And now, because these two logarithms have the same base, they can condense to a single logarithm that has a fraction in its argument. And I'm going to use a property of exponents. And instead of writing y squared z squared, I'm going to write it like that because it's even smaller. Look at all that. Isn't that fun? That's fun, right? Yes, Mr. Evans, it's a lot of fun. I knew you'd love it, nerds. I appreciate you.